Hi everyone, welcome to lecture number 3 for Physics 151. The topics for this lecture involve the sort of basic quantities of one-dimensional kinematics. And by kinematics, we mean the quantities involving the motion of an object. So the topics today involve position, displacement, and distance traveled, which are all quantities relating to the position of an object. Average velocity and average speed, which are related but different. And then what graphs look like and how we interpret those graphs of those quantities. And this topic will continue over into lecture number 4. The related parts of our textbook are sections 2.1 and 2.2. And in today's lecture, I'm going to include some examples from tutorial number 3. And the topics in today's lecture relate to online homework number 3. So from now on, I expect to sync up these numbers between the lecture number, the tutorial number, which are the sample problems, and the online homework number, which is problems for credit. But before we get started, let's first do a quick review of some of our topics from lecture 2. So just to see if you remember how to round off, how to identify significant figures, and where to round off significant figures when we do multiplication or addition. So pause the lecture right now, try and answer these 4 questions, and then we'll quickly go over the answers. Okay, so I hope you tried to answer these 4 questions. And very quickly, let's talk about how to answer these. So first of all, how do we identify which digits are significant? Well, when we have a quantity that's already in sort of a standard scientific notation form, meaning that the decimal point comes after the first non-zero digit, like it is here. This is what I referred to previously as the conventional most compact form. If we've already expressed a number in that way, a value in that way, then all of the digits that we write here are all significant. So therefore, that looks like 4 digits, a 1, 6, 0, and 9. So there's 4. What about if a value is not already in that sort of most compact scientific notation form? Well, one way to do this is to transform it into that form. So it looks like in order for me to get this into scientific notation, what I would need to do is move this decimal place 2 positions to the right. So right now it's located here. I'd want to move it 2 positions to the right so that it follows the 5. So what would that look like in scientific notation? That would be 5.010 times 10 to the negative 2, because I moved the decimal place 2 positions to the right. Now, do I need to write this last 0 over here? The answer is yes, I do. Because the only reason it's there, that trailing 0 is there, is because it was measured. So therefore, we do need to write it. So now we follow our rule, and our rule says, well, I look at the value now that it's written in this most compact form, this sort of proper scientific notation form, and all 4 of these digits must be significant. So the answer is 4. Another way to think about this one is to think, which is more complicated, is to think about the rules for when digits are significant or when they're not. And the answer for that is, well, okay, if it's not a 0, then it is significant. So this 5 is significant and this 1 is significant. But if it is a 0, then there's a whole set of rules about whether it's significant or not. And in short, for this example, the trailing 0 here, yes. The only reason it appears is because it was measured. So in other words, the next digit isn't a 1 and the next digit isn't a 9, it's a 0, which is in between the 1 and the 9. This sandwich 0 here is sandwiched between 2 other significant digits, the 5 and the 1. So it is also significant. However, these preceding zeros right here, these 2 zeros that come in front are not. This one is a placeholder. So its job is to move the decimal place over to where it should be, over to the left. And then this very first one here is just cosmetic. Its whole job is just to make the decimal point easier for our eye to see. So when all is said and done, then it looks like this is going to be 4. Okay. Now when we have multiplication or division, what we need to do is we need to identify the number of significant figures in each of the values that are being multiplied or divided, and then find the lowest of all of those numbers, right? In other words, which number is the least precise, which number is known the most crudely. So when I look at this first digit, this first value right here, I can see that this has 4 significant figures. And then I look at the next value, and I see that it has 2 significant figures. So which of those is known to fewer sig figs? In other words, is known less precisely? And the answer is 2. 2 is the smallest. So therefore, I need to round my final answer to 2 significant figures. So when I ask my calculator, what is 8,090 times 0.0042, my calculator tells me the answer is 33.978. And then my calculator might stop there, but what's understood is that there's a whole bunch of additional unwritten zeros, right, that trail after that on the calculator screen. So where do I round this off? I round it off to 2 significant figures. So that means I must round it off to this place right here. So the answer is just 34. For addition and subtraction, the rules are a little different. It's not a matter of identifying how many significant figures are in each of the values that I'm adding or subtracting, but where is the last significant decimal place for each of those values. So for my first value, 10.101 grams, then I see that this last digit here is still significant. So notice that this is in the thousandths place, right? It's the 3rd digit after the decimal point. What about in the second value, 0.02020? Well, I can see that the last significant digit is here in the 10,000ths place. Okay, so which of these now is less precise? Because that's what I want to round my final answer to. Which of these occurs in the higher decimal place? And the answer to that is the thousandths place. So I want to round my final answer to the thousandths place. So when I ask my calculator, what's 10.101 plus 0.02020? My calculator tells me the answer is equal to 10.12120, and then the calculator actually stops after the 2, but I know that there's an infinite number of trailing zeros that I can use as needed. And once again, I go back to the question of, okay, which digit do I want to round off to? And the answer is, I want to round to the thousandths place. So that's this digit right here. So my answer is going to be 10.121. Another way to think about this is if I were to stack the values vertically like an old-fashioned addition problem. So what would that look like? 10.101 plus 0.02020. And I can only do this if I have these both in the same units and both to the same power of 10. And then I do the addition problem this way. Okay. Now, let's ask the sig fig question again, right? The sig fig question says, okay, which is the last significant figure for each of these 2 values? And I can see that in the first value, the last significant figure is in the thousandths place. And in the second value, the last significant figure is over here in the, it's actually the 100,000ths place. I'm sorry, I said 10,000ths before, but this is 100,000ths place. So what that means is when I go ahead and do the addition, sorry, I got to write it a little bit lower, 0.12120. Then what I'm going to do is I'm going to round to the thousandths place. I want to round off to this place, which is that 1 right there. So I round this off to 10.121. Okay. And why? And let's reflect on this for just a moment. Why should this be the case, right? Instead of just sort of following a rule, which is maybe where we learned it initially, let's think about this scientifically for a moment. If we have a value that is known relatively crudely, right? So this first value here is only known to the nearest thousandth of a gram or milligram, and I add to that a value that's known much more precisely, right? 100 times more precisely. So I'm going to add to it a value that's known to the 10,000ths place or to the nearest hundredth of a gram. Okay, so I'm adding a value, a milligram. So I'm adding a value that's known to the nearest milligram, and I'm adding to it a value that's known to the nearest hundredth of a milligram. How well should I know the sum of those two masses, right? In other words, if I'm in chem lab and I have 10.101 grams of one substance, and I add to it a very precisely measured, very small amount of a second substance, how well do I know the mass of the combined amount? And the answer is I only know it as well as I knew the mass of the first amount. Okay, if I add a crudely known quantity to a mass, in this case, a crudely known mass to a precisely known mass, then I know the sum or the difference, if we're doing subtraction, only crudely. Okay, it wouldn't make sense for us to gain additional precision off to the right over here when I add a crudely known measured quantity to a precisely measured quantity. So instead, we only can know the sum or the difference to as well as we know the crudest of the values that we're adding or subtracting. Okay, great. All right, so let's start our new topic. And the topic is that let's start with position and position-related quantities. In this case, displacement and distance traveled. So, first of all, what is position? What do we mean by position when we say that? Well, we mean the location of something in space. And what we're used to using as a way of designating the location of something is its position along a coordinate system. So in one dimension, we're just going to use x, which is our familiar x-axis, right? Where x equals 0 at a location that we'll call the origin. And for many problems, we will get to choose where the origin goes. And for a few problems, the origin will be given to us. Okay? For two-dimensional problems, we have an x and a y position, or if we wanted to, and it'd be better for us, we could use polar coordinates like r and theta. And for 3 dimensions, we're going to have an x and a y and a z position, although we won't have very many of those problems in physics 151, if any, really. And then there's other three-dimensional coordinate systems that are introduced in classes like Calc 3 and Calc 4, like spherical coordinates and cylindrical coordinates. We're going to stick to Cartesian coordinates for this class. So we're going to do a lot of one-dimensional and two-dimensional problems. So we're going to have x and y. And although there will be times when we will define them differently, most of the time, x will mean position along a horizontal axis. So when we have a projectile problem, for example, x will be how far horizontally has an object traveled, or what is its position horizontally. And y will be what is its position vertically. Displacement is a change in position over time. So we designate that change with this capital Greek delta in front, as I'm sure you're familiar with from chemistry and many other classes. But I want to say that as a physicist or in physics class, every time you see that delta, I always want you to think later minus earlier, okay? It's really important to think of delta is always equal to later minus earlier, final minus initial, or some later time minus some earlier time, which we could call position 2 and position 1. But notice again, it's the later position that comes first, and we subtract from that the earlier position. Or sometimes we'll call the later position the position at time t, which is some later time, and from that we'll subtract some original position, which we often designate x sub 0, although we often pronounce that 0 naught, using sort of a British pronunciation for the 0. Okay, so x naught. You'll hear physics teachers and mathematicians say that all the time, x naught. Right? What do these all have in common? They're all a later time minus an earlier time. Okay, so in other words, we always want to know how far something has traveled. Well, we want to know what its change in position is over some time span. Now, if an object moves in the positive direction, right? Because remember, our Cartesian coordinates, each of these sort of directions, the x direction or the y direction, they have a positive direction and then a negative direction. So the positive if an object moves over time generally in the positive direction, then we would say that its displacement is positive. And you'll find that when you do that subtraction between the two positions, you'll wind up with a positive value. If an object moves in the negative x direction or negative y direction over time, then its delta x or its delta y will turn out to be negative. And sure enough, when you do this subtraction, you'll find that the delta x or delta y turns out to be a negative quantity. So that means displacement can be positive if an object's net motion is in the positive direction of x or y, and the displacement can be negative if an object's net motion is in the negative direction of x or y over time. Now, there's a third quantity that we use in some of our formulas, and that is the distance traveled by an object. Okay? Now, distance traveled is the distance that is traced out by an object over its path. So if you're driving a car, then imagine, looking at like how much the odometer increases over time. Okay, and let's assume that if the car goes in reverse, the odometer still goes up. Okay, so don't let's pretend it's a car whose odometer can never run backward. So in other words, it's how far has this object traveled along its path or along its surface. So you could have a path that is in 3 dimensions in space or in 2 dimensions along a surface, and it can follow a curved path. It can follow a bunch of, sort of right angle turns. For now, we're going to deal with one-dimensional cases first. So an object that can only move back and forth along the x-axis. Now, it makes sense that the path length or distance traveled that an object has traveled can only be positive, right? It's impossible for you to trace out a negative distance through space, right? You can be at a negative position when you're to the left of the origin. You can have a negative displacement if you have moved in the negative x direction over time. But in all of those cases, you've worn more rubber off the bottom of your tires, or you've worn more off the bottom of the surface of your shoes if you've traveled any distance through space, whether it's in the positive direction or the negative direction. So the distance traveled in that sense can only ever be positive. So we can ask ourselves, in which circumstances is the distance traveled the same as the displacement? Okay. Well, in general, it is a general case that the distance traveled is the absolute value of the displacement for a straight line path, okay, if the object never changes direction of motion. So in the case of a straight line path in one dimension, right, so no curvature through space, so not like a projectile that curves its path as after we throw it or launch it. And as such, you can't change the direction that you're traveling. So even along a straight line road or a straight line path, the object can never reverse during our time interval over which we're calculating this delta. If both of those things are true, then what you'll find is that the distance traveled is going to be the absolute value, at least, of the displacement. And if the displacement happened to be forward in the positive x direction, then you'll find that the distance traveled and the displacement are exactly the same. What do you do if, in fact, an object has a change in direction of motion? So suppose you have a car on a straight line road, but the car reverses or goes backward at some point during our delta t. Or you have an object in 2 dimensions or 3 dimensions, and it has a path that changes direction. So it either turns through some angles or curves. In that case, the long and the short of it is there is no one standard formula to find the displacement for any of those cases. I'm sorry, distance traveled for any of those cases. There is no one standard formula. In fact, as you may know, if some of you have had calculus 2, the integral that you must do to find the path length over a curve is complicated and difficult. So we have to just figure it out case by case with a custom calculation. Now in this class, we're never going to do really complex curves. The most that I might ever ask you to figure out the path length over would be a path where there's a bunch of straight line segments, right? So that are connected, or maybe a path that's circular, where we all know the circumference of a circle or the arc length along a circle from trig class. So in that case, we know formulas to find the distance traveled. But for more complicated cases, like if there's a roller coaster going down some curvy track, then there's not I'll either give you the path length traveled, or we won't need it for the problems that we'll do in physics 151. Now, this also, if we look at these definitions, it raises another interesting question, right? Path length traveled can be complicated, right? Or distance traveled can be complicated, and it clearly depends on the length of the path taken, okay? However, if you look at the definition of displacement up above, you can see that it really depends only on your starting position and your ending position, right? And it doesn't depend at all on the path that you take to get from the starting to the ending position, or whether you speed up and slow down in between. All it really depends on is where you are at the start of our time interval and where you are at the end of our time interval. And in 2 dimensions or 3 dimensions, that is also true. All that the displacement depends on is what your x and y are at the start, and your x and y are at the end, or x, y, and z at the start, and x, y, and z at the end. So what that means is displacement is a path-independent quantity. It's independent of the path taken. All it depends on is the starting and the ending locations. Okay? Whereas distance traveled totally depends on the path taken, and as a result, it can be quite complicated to calculate. This idea of quantities that are path dependent and path independent is going to come up in a couple of slides as we talk about velocity versus speed, but it's going to come up later when we talk about quantities that are conservative forces versus non-conservative forces. Right? The amount of work they do, the amount of work that conservative forces do does not depend on the path taken, whereas the amount of work that non-conservative forces do does depend on the path taken. So tuck that away in the back of your mind for a few chapters for when we get to work and energy. So let's just do a couple of really quick examples taken from our textbook of displacement, of calculating the displacement if you're given 2 positions. So notice in this example here, we're given the position of a race car in the first example at some initial time, which we'll call time t1, and at some final time, which is time t2. So we have 2 positions. We have an initial position and a final position, which I renamed x initial and x final, or we can, the textbook called those x1 and x2. Right. How do we get the displacement then? Remember what the delta is. The delta is always the later minus the earlier position. So we have the later position minus earlier position. So you could also call that x final minus x initial. And you'll probably see me use the final and initial notation more than the 2 and the 1 notation. 2 and 1 is used a lot in math class. You might recognize that from, when you calculate the slope of a line. But a lot of times that can be a little confusing because it implies that something has a value of 2 and something has a value of 1. Whereas final and initial, just it's left open-ended. Final is later, initial is earlier. So we plug those values in, 277 meters minus 19 meters. So notice that's the initial position, the final position minus the initial position. And I asked my calculator what that is, and it's 258 meters, and it's positive. Now, you never need to write this plus sign on any positive quantities, but once in a while, like now, I'm going to write it just for emphasis. Okay? What does this tell us to see that the displacement is positive? What does that tell me? It tells me that the object moved in the positive x direction over that time interval. It had net positive motion over that time interval. Now notice, we don't need to know anything about whether this race car speeds up and then slows down, or whether it went at a constant speed, or whether it even paused in the middle, turned around, and then went forward again. All we know is that at an earlier time, well, actually the times are given up here. At an earlier time of 1 second, it was at a position of plus 19 meters, and at a later time of 4 seconds, it was at a position of 277 meters. And that's all we need to know to get the displacement. So notice again, displacement is path independent. It doesn't matter whether the object just travels forward only or whether it doubles back and goes forward or if it speeds up or slows down. And in 2 or 3 dimensions, it wouldn't depend on whether the path is a straight line or if it meanders in some way. Okay, now let's take a quick look at the second example. For the second example, same sort of thing. This is a truck that goes in the opposite direction at a very different speed. Okay, so at some earlier time, t1 of 6 seconds, the starting position is plus 277 meters. And at some later time, 16 seconds, the final position is plus 19 meters. So how do we calculate the displacement in this case? Again, displacement is equal to x final minus x initial, or x2 minus x1. That's the position at the end, which is 19 meters, minus the position at the beginning, which is 277 meters. And in this case, it's negative 258 meters. Okay? So what does that negative sign tell me then? That tells me that this object moved in the negative x direction, or had a net motion in the negative x direction over this time interval, over this delta t, whatever that might be. Okay, so there was a net motion in the negative x direction. By the way, nature doesn't lay out axes in space for us, so we get to choose. If you have a straight road, then we get to choose in order to solve a problem to lie our x-axis along that straight road. And where we get to put the origin also can be a matter of choice as well. We can choose the origin to be one of the endpoints of the travel, and that's often convenient and mathematically simpler. Or sometimes the origin has some natural position that we think it should go, right? For example, if a meter stick is involved in the problem, we will often put the origin at the 0 point on the meter stick, for example. Okay, so let's take a quick look at tutorial number 3, problem 1, which has a sort of a similar example problem. You have a car on a straight road, only now there's 3 time intervals. So notice there is a time interval A, which I'll call 0 to 5 seconds. And the car's position goes from negative 50 to positive 150 during that time interval. Then during the next time interval B, it goes from 150 to 120. And then during time interval C, it goes from 120 to negative 20, okay? So what that means is we can imagine that we have some sort of straight road, and we're gonna lie our x-axis, we're gonna, along that straight road, there's an origin somewhere. And then we have a car that travels back and forth along that road. And that car starts over here at some initial time, at some negative position, right, negative 50 meters. And then the car travels all the way over to positive 150, and then it doubles back to positive 120, and then it doubles back even further to negative 20. And it could have even more complicated motions in between there at this point that's not specified. Although you're going to see coming up that I'm going to simplify things and just say, let's pretend that it's very simple motion and that it doesn't double back or loop around. Okay, so knowing all this, let's calculate what is the car's displacement over any one of those time intervals. So let me just start with interval A. I don't think I'll have room here or time to do all 3 of those. But if we think about time interval A, then the displacement over time interval A is going to be equal to x at the end of time interval A. So that's x, I'm going to call it x final minus x initial. That's x at 5 seconds minus x at 0 seconds, okay? And if I look up at my start of the problem, I see that the position at 5 seconds is 150 meters. The position at 0 seconds is negative 50 meters. And then I do that subtraction, and the answer is positive 200. Okay. Once again, you don't need to write the plus sign yourself, but I'm going to write it here for clarity. All right. So notice, watch your algebra. We are subtracting a negative value here. So we get an even bigger positive quantity. All right, so the car's displacement during that first 5 seconds was positive 200 meters. So the positive sign again means it's in the positive x direction, that displacement. How about over the entire 15-second time interval? So if I want to know the position, oops, let me erase that. If I want to know what the car's displacement is over the entire 15-second time interval, I can say, okay, I'll just call that delta x total, which is A, B, and C all together. And again, that's going to be its position at the end of the whole time interval minus the position at the start. So that's x at 20 seconds, oh, I'm sorry, 15 seconds, minus x at 0 seconds. And that's going to be the position at 15 seconds is negative 20 meters. Use extra parentheses whenever you need to make your math clear, minus the position at 0 seconds. And I ask my calculator, or I can do this one in my head, negative 20 minus negative 50 is positive 30. So I'll leave it to you to try the other ones. And so press pause until you've calculated the displacement during time interval B and during time interval C. Oh, by the way, let's reflect on this for a moment. So the car's total displacement then from the start of its entire trip to the end of its entire trip is going to be positive 30 meters. So if I go up to my little sort of sketch up here, then I can see that, yes, is that true? Yes, at the start of the whole trip, it's at negative 50, and at the end of the whole trip, it's at negative 20. So I can see that its net displacement over this whole time interval is going to be like this, positive 30 meters. That's the net displacement. Now, did it go there in a direct straight line path? No, it didn't. Over the whole 15 seconds, it went way off to the right, way all the way out here to 150 meters. Then it doubled back a little bit to 120, and then it came all the way back to negative 20. But when all was said and done, what was the sort of net displacement at the end of everything? Positive 30. So these are the answers for once you've calculated A, B, and C and the total. Let's examine those same two time intervals and calculate the distance traveled during each of those. So distance traveled. In general, for a straight line path, when an object doesn't change direction, okay, so as long as the car, during the time interval that you're interested in, if the object doesn't change direction, then we can say that, all right, then we can use the general formula that, so if, I just want to spell this out again, if we have a straight line path and no change in direction, okay, then we can say that the distance traveled is just the magnitude or absolute value of the displacement during that time interval, okay? So then we can use that expression right there. What if the object does change direction? Well, then there is no formula, and you just have to look at the problem and try and just figure it out based on the specifics of that case. So I'm going to make these simplifying assumptions here that the car moves only forward during time interval A and only backward during time intervals B and C. So what that does is it allows us to satisfy this no change in direction during each of the time intervals individually. So it just sort of make things simple for us, and we can use that expression. So in that case, what is the distance traveled during time interval A? Well, it'll be equal to the absolute value of the displacement during time interval A. And in the previous problem, we calculated that to be positive 200 meters. So the absolute value of that is just 200 meters. So all of these distances need to always be positive, right? So notice a lot of these answer choices have a bunch of negative values in them. Yeah, that's all just nonsense. So we can immediately eliminate those, right? Distance traveled always have to always be positive. Again, you can't unwear the tires on your car, right? It doesn't matter whether your car is going forward or in reverse, it's always going to wear the rubber off the tires. So distance traveled is always positive. Okay. For time interval B, again, assuming that there's no change in direction, that's going to be the absolute value of negative 30 meters. So that's positive 30 meters. And we can do time interval C as well. And I'll let you try that. All right. What about the total distance traveled over the entire 15-second time interval? Okay, so here we don't have a simple formula because the car does change direction at least once during that entire 15-second time interval. In fact, it does change direction at t equal 5 when it gets out to the extreme end of its travel. So we just have to break it down. We just have to sort of think about it. And what we can quickly realize is we can use this, we can just come up with our own custom formula and say, okay, d total is going to be equal to the sum of all the distances traveled during each of the 3 legs of the trip. So we can use what we calculated in the previous part and come up with that total. So pause the video right here. Try and find out what the distance traveled is during segment C, and then calculate what the distance traveled is during the total trip. And then check your answer, and then unpause and check your answer. Okay, so the distance traveled during time interval C is 140 meters, and then the total distance traveled is the sum of those 3, which is going to be 370 meters. All right, let's talk about velocity, and then on the coming slide, we'll talk about speed and why we distinguish between the two, or what we mean when we distinguish between the two in physics. Velocity is a rate of change of position, right? Put in sort of common language. And the way we can define that more mathematically in a formula is to use the expression the amount of change of position we know better now as displacement. So that's what displacement is. It's the amount of change of position between some earlier time and some later time. If we divide by the amount of time that elapses during that interval, then we get a rate of change of position. Now, if all we know is the starting position and ending position, and we don't know anything about the path in between, then what this gives us is the average velocity over that whole time interval. Okay, so this is the definition of average velocity over some time interval delta t. Our textbook uses AV as a subscript. Other textbooks spell it out, AVE. You're welcome to do that too. Other textbooks use a bar over a quantity to denote some average value of that quantity over time. Now, if we think about this, then this formula looks a little familiar, doesn't it? When we see one delta over another delta, this rings a bell from algebra class when we think about a line, and we think about the formula that we use to calculate the slope of a line. So, sure enough, that's exactly what this formula would give us if x varies with t like a straight line. This would give us the slope of that straight line on a graph of position versus time. So the numerator is what's on the vertical axis of your graph, and the denominator is what is on the horizontal axis of your graph. In fact, you might remember this slope formula as being the rise over the run. Okay, so vertical change over horizontal change. So if we were to graph position on a vertical axis and time on a horizontal axis, average velocity would give us the average slope over some time interval delta t. And if our velocity is a straight line, then it's the slope of that line. If our velocity is not a straight line over time, then this gives us sort of the average slope between 2 points, right? You can have a graph that follows some more complicated curve, and this will just be like the sort of average tiltiness of that curve, right? Average steepness, I mean, of that curve. What if we were to shorten the time interval to be extremely brief? So instead of delta t being a long time interval, what if delta t were to become so small that we could barely even see it on the graph? In that case, t2 and t1, or t final and t initial, just become the same value t, and that becomes an instant in time. And the slope then, instead of being an average slope over some time interval delta t, just becomes the instantaneous or tangential slope at that moment. So again, if we had a graph of x versus t, position versus time, then the instantaneous velocity is the tangential slope at any point on that graph. In calculus, we call taking the delta x, the delta of one quantity over the delta of another quantity, and then shrinking the delta down to an infinitesimal amount, we call it taking the derivative. So as I know at least half of you have taken Calc 1 already, and you know then that the derivative is the slope of a graph at any point on that graph. So the instantaneous derivative at any point on a graph is the slope. So in fact, in Calc 1, you probably already learned that the instantaneous velocity of any object is the first derivative of its position. So I just want to remind you of that definition. If you know that already, you're welcome to use it. However, this class does not require calculus, and I'm never going to use this formula, this formulation in solving any of our problems going forward. We will learn some formulas for instantaneous velocity for objects in special cases. So there will be some special cases of an object moving with a constant acceleration, for example, or uniform circular motion or simple harmonic motion, where we'll learn formulas for the instantaneous velocity of a graph. But in general, we won't have a way to find this without calculus. It requires calculus to find it in general. So in general, for this class, the only sort of formula we can sort of quote unquote know is average velocity. Okay. Now, in common English and common parlance, we generally use the term velocity and speed interchangeably. However, in physics, we distinguish them a little bit. Velocity is, like I said, the rate of change of position over time, and we know rate of change of position, better known as displacement. However, average speed is going to be distance traveled over time. Now this is interesting, okay? So average speed isn't necessarily going to be the same as average velocity unless we're in the special case when the distance traveled is the same as the displacement. So do you remember what that situation was? Okay, so under what condition was that true? Okay, so you may remember that, so I'll let you look back at the previous slide actually and check that out. So feel free to back up in the video or hit pause. Okay, you should have seen that it was when the object follows a straight line path and it doesn't change direction of travel during the time interval delta t. In that case, distance traveled and displacement will be exactly the same, and average speed and average velocity will be exactly the same to within a factor of -1, okay? So distance traveled might be the negative of, I'm sorry, displacement might be negative, but distance traveled will be positive. So there might be a minus sign there, okay? All right, so remember, distance traveled is always positive only. If we shrink down the time interval to just an instant, then we have instantaneous velocity, and instantaneous speed is, again, just the positive version of instantaneous velocity. By the way, notice that average velocity doesn't depend on the path that you take. So in 2 dimensions or 3 dimensions, or in 1 dimension even, if you turn around or reverse during that time interval delta t, average velocity depends only on the starting and ending positions, but average speed totally depends on the entire path length that you travel during that trip. So it does depend on the path you take and whether you double back or reverse more than once. And that all boils down to, and the answer is why, it all boils down to whether the distance traveled or the displacement depends on that. So bear that in mind. It will often be the case that, except for the very simple case of an object moving only along a straight line and only moving in one direction, like only forward or only in reverse and never doubling back. That's the only time that the average speed and the average velocity are going to have the same value, at least to within a factor of -1, right? One might be the absolute value of the other. Otherwise, the average speed and the average velocity will often be different because it's the distance traveled and the displacement that are different, not the times. The times will almost always be the same. Now, just a quick word about notation. Once we get to two-dimensional kinematics, then we're going to change our notation. Velocity, instead of always just being a plain letter V, will be a vector in 2 or 3 dimensions. In this class, mostly 2. And vectors have horizontal and vertical components, or x and y components. And so when we want to talk about the velocity of something, the horizontal velocity of something, we usually won't mean the entire magnitude of the velocity. We'll usually just mean the horizontal component only, or the vertical component only. So we will use these components a lot instead of using the total speed of an object. Mostly because you'll see the formulas that we deal with use the components a lot more than they use the total speed, the total magnitude of the total velocity. Speed is defined as the magnitude of that whole velocity vector. How fast is the object moving through space total in any direction? And the way we're going to write that will be just a plain V. So it'll be a V without the vector hat on top. So when we get to projectile motion later in chapter 2, we're going to revise our variable for speed from S to V. So just plain V without a vector hat on top, without subscripts, will become speed. Okay, so later when we get to projectile motion, keep that in mind. We're not going to use S anymore, right? S will be used for other things, maybe path length, or once in a while it might be used for, other quantities. Okay, rarely will it be used for speed after this unit right now. So I'm going to use it for now for lectures in 3 and 4 and 5. We'll use S for speed for now, but not for much longer. All right, now that we've learned those definitions for average velocity and average speed, let's put them to use and you do some of the remaining parts of problem 1, and then I'm going to solve with you problem 2 as an example, and then I'm going to leave the remaining stuff, problem 3, to you for additional practice. At any point, once you get the hang of this, feel free to go to our online homework problems that are worth credit and work on those. Okay, so first of all, going back to our same car problem in problem 1, what is the car's average velocity during each of the time intervals A, B, and C, and then over the entire time interval? So we have A, B, and C, and then over the entire 15 seconds. And then what is the car's average speed during each of those same time intervals, and then over the entire 15 seconds? And we're going to compare those and see if they're the same or not. Okay. So in order to answer this, you're going to have to look back. Well, let's write out the formula first, and you'll see. Okay, so our formula for average velocity in general is, displacement over time for whatever time interval we're interested in. So if I'm only interested in time interval A, then my average velocity over time interval A is going to be equal to the displacement over time interval A divided by the time that elapses during time interval A. Now, I could calculate this from scratch, but I think I already have this quantity from the earlier part of the problem, right? So look back at part A, and you'll see that the displacement during time interval A was equal to 200 meters. So I'm just going to use that because we already found it. And then the time interval, we have to, well, if it were more complicated, this would be a more complicated calculation, but it's going to be 5 seconds minus 0 seconds, right? Or 5 seconds. Notice how time intervals are always positive, right? Our clocks never run backward, ever. So that's going to be equal to positive 40 meters per second. Let's do one more of those. Average velocity over time interval B. Sorry that my handwriting with the stylus is not the best. Okay, so looking back at part A of the problem, we calculated that the displacement during time interval B was negative 30 meters. And then what about our time interval? Well, that's going to be equal to 12 seconds minus 5 seconds. Okay, and there's an extra sig fig there that I'm just not writing, just so I can squeeze this into the space I have. So that's going to be negative 30 meters divided by 7 seconds, right? I ask my calculator what that is, and I get negative 4.3. It's a repeating decimal, so I round off to 2 sig figs. So it looks like a 2 sig fig problem. So negative 4.3 meters per second. What if I want the whole time interval? Oh, pardon me, not interval C, but the entire time interval. So that's going to be equal to the displacement over the entire time interval divided by the time of the entire time interval. So again, we already calculated this in 1b, and the displacement over the entire time interval was positive 30 meters. And then the entire time of the entire time interval is 15 minus 0, or just 15 seconds. So that's equal to an average velocity of positive 2 meters per second over the entire time interval. Okay, so I can, just for the moment here, let me circle my answers. So D was my answer to the second one. And after you calculate the 3 values in the first one, you'll see that it's C. Now let's calculate some of the average speeds. I'm going to change my color here. Okay. Average speed over time interval A is going to be equal to distance traveled over time interval A divided by time of time interval A. And distance traveled, in this case, is the same as the displacement. So in this case, it turns out to also be 40 meters per second. All right. So that's interesting. This is the same in these two cases because, why? Because this is a simplified case. Remember, I have that stipulation that the car doesn't double back, doesn't switch direction during any of the individual time intervals, A or B or C. It only travels in one direction only during each of those time intervals. So during time interval A, it's forward only. So notice that the velocity is positive, and then the speeds are always positive, whether the car is in drive or reverse. The velocity is positive because the car is going forward. Okay. Now, if we calculate the speed for time interval B, average speed is going to be distance traveled during time interval B divided by time, and that's going to be equal to, now the distance traveled during time interval B was a positive 30 meters, not a negative 30 meters. And so that's positive 4.3 meters per second. So notice that in this case, speed always positive, has to be, right? Because distance traveled is always positive. But the velocity was negative because the car was moving in the negative x direction during that time interval. Okay? So their absolute values are the same because the car doesn't reverse direction, right? So that's all of our distance traveleds are just the absolute values of all of our displacements. So therefore, all of our speeds are just the absolute values of all of our average velocities, average speeds and average velocities, because the car doesn't reverse direction, doesn't switch direction during any one of the time intervals, only at the breakpoints between the time intervals. But let's now take the case of the entire time interval. Does the car change direction during the entire time interval? Yes, it does. So now we expect that, distance traveled for the entire time interval, you might remember, we just calculated it before, was very different than the displacement over the whole time interval. So we're going to expect now our average speed to be very different than our average velocity. And sure enough, average speed over the whole time interval is distance traveled over the whole time interval over the time of the whole time interval, right? And that was equal to positive 370 meters divided by 15 seconds. I'm going to ask my calculator what that is. That comes out to 24.7 meters per second. Now, I can make an argument that I gained a sig fig here through addition. So I'm just going to keep that third sig fig. Okay. But if you round it off to 2 sig figs, that's fine. Okay. So notice how very different this answer is than the answer for the average velocity up above. In fact, that deserves red. Okay, so average speed, so to reflect here, average speed over a time interval where the object changes its direction is going to be different than average velocity. Okay, so if you have to calculate any additional parts, press pause now, and then I'll show you all the answers quickly, and we'll go on to question 2. Okay, and then going on to question, oh, I forgot there's one more part to problem 1. And that is, let's take all of this position stuff and try and make a graph out of it, and then think about the graph for a moment. So this is sort of foreshadowing lecture number 4, okay? All right, so let's graph the car's position versus time over the whole 15-second time interval. So all you have to do now is no further calculation, just look at the very initial list of positions versus time that appeared at the very start of the problem. I'm sorry, I should have reproduced them here. Okay, so the car's very first position at time t equals 0 is -50. So let's graph that on here. Okay, so we have, yeah, I guess I'm going to move it just a little lower. Okay. All right, so this position right here is going to be -50 meters. Again, position is along the vertical axis here. So this is the car's horizontal position along a road, but we're graphing it on the vertical axis. The horizontal axis here represents time. Okay, so this is at time t equals 0. Then we know that at a later time, at 5 seconds, we are just told in the way the problem is laid out that the car has moved all the way to positive 150 meters. So the car's position is up there. Okay. Then we know that at 12 seconds, notice I'm trying to make this sort of accurate, right? Sort of to scale. The car's position has changed to the car's position has changed to positive 120 meters. Okay, so I'm just drawing these little sort of guidelines here. If this were graph paper, we wouldn't need that. And then finally, at 15 seconds, we know that the car's position is at -20. So -20 meters. And that's the car's final position, okay? So those are the car's 4 positions. All right, now how do we connect these 4 positions to each other? Well, that's a good question. If all you read was the very first part of the problem where it just describes the car's positions at 4 times, then you wouldn't know what does the car's position look like as a function of time between each of those 4 points. We need more information in order to be able to tell that. But then we're told later, first of all, the car never reverses direction. So therefore we know, oh, the graph has to be sort of, monotonically increasing between these first 2 points, and it needs to be monotonically decreasing between the next 2 and the next 2. So it never switches around. It doesn't go further forward and then double back or something, or reverse, forward, reverse sort of thing. It's forward only, reverse only, reverse only. And then we're told right here that make the yet further assumption that the car's velocity or speed remains constant. So, that the car's velocity or speed remains constant. So what that means is it lets us know that the rate of change of position during each of the time intervals is constant, meaning regular. It has a regular value or same value over that whole time interval. Oh, so that means think about that for a sec. Rate of change of position means that for every second that passes, this car is going to move the same number of meters in its position. So during the first time interval, this car is going to have some constant rate of change of its position. Then during the second time interval, it's going to have a different but also constant rate of change of position. And then during the next time interval, another different but constant rate of change of its position. So what that should look like on a graph then is we would expect that the rate of change of position, right, for every second that goes by, the car should increase its position by the same amount. And another second goes by and the car increases its position by the same amount. So, oops, I got a little ambitious there. But let me try that one more time. And if I were to slice this into tenths of a second, like this, if I were to slice it into hundredths of a second, then what you would wind up with is just a continuous line like that. Okay? That's a car whose position is changing by the same number of meters every fraction of a second that goes by during that 5-second time interval, during this entire 5-second time interval. The same would be true for the next time interval. In other words, the rate of change of position with respect to time will be smooth and linear. And then during the last time interval, the rate of change of position with respect to time will be smooth and linear. And finally, I have a thought question down here. What do you think the value of the slope of this graph is supposed to be during each of those 3 time intervals? Well, the slope of that graph is going to be the rate of change of position with respect to time, right? Position with respect to time. So slope should be change in position, right? Rise over the run, change in position with respect to time. Well, what does this formula look like? It should look like average velocity, right? So we know the average velocity over time interval A, over time interval B, and over time interval C. So sure enough, the slope of this graph during each of those time intervals should be equal to the average velocity that we calculated before. So that means that the slope during this first time interval is going to be equal to the average velocity during that time interval, which is positive 40. And notice the units of the slope are the units of the rise over the units of the run, which is position over time. And then the slope of the next segment was equal to the average velocity during the next segment, which was negative 4.3. And then finally, during the last segment, the average velocity was negative 47 to 2 sig figs. All right. So again, this is foreshadowing lecture 4, but I just wanted, since we've seen already now the formula for average velocity, I wanted to sort of tie this all together. Okay, let's take a look at problem 2. Problem 2 shows you a completed graph of position versus time. So we just constructed a graph a moment ago for the problem 1. And now this shows us a graph of position versus time that's already given to you. And then it asks you, okay, what is, well, first of all, parts A and B ask you to interpret this graph. What does it mean for the motion of the car, if this is a little toy car along a straight track? And then part C onward asks you to then calculate average velocity and average speed for some of the parts of the graph or for the entire graph. So let's start with A and B, okay? When you look at this graph, let's remind ourselves once again that this graph is showing us position on the vertical axis versus time on the horizontal axis. So when you're asked a question, during what time interval is the little car at rest? And again, assume that the track, the positive x direction, I'm sorry, the x axis lies along this straight track, so the car can move along the x-axis. And let's define the forward direction or drive to be in the positive x direction. So reverse would be in the negative x direction. Okay, all right. So if the car is at rest continuously over some period of time, then what should its value of its position do as time passes? What would we expect its position to do? Well, if it's at rest, its position should be steady, constant, and unchanging as some amount of time passes, right? An object can be instantaneously at rest. Like if you throw a baseball straight up, then there's a moment at the very top of the arc where it's momentarily at rest, but right before that and right after that, it's in motion, right? And a car or other object can do the same thing, perhaps, as well. So that's also possible, right? But in this case, we want to know, okay, when is this car at rest? It is when the position is unchanging over more than an instant of time. Okay. Or it would be at, I guess, if you think about the baseball, then it is at an instant where the velocity is going from positive to negative or negative to positive. So that would also be that is also when an object is instantaneously at rest, is right at that transition point between a positive and a negative velocity or a negative and a positive velocity. All right, so let's consider the continuously at rest. So continuous rest would mean that position has a constant value over time. So do you recognize any locations on this graph where that's true? It looks to me like that would be this segment right here, where the car's position remains parked at positive 3 meters. Notice how the car just sits at positive 3 meters for a full 4 seconds. And then, anywhere else? It looks like there's another segment of the graph down here where the car remains parked at negative 3 meters. Okay? So in both of those segments, the car is just sitting motionless at a particular position. Are there any moments here where the car goes from having a positive velocity to a negative velocity? So in other words, those would be moments of instantaneous rest. Well, I don't see those on this graph. That would be when the graph goes from a positive slope to a negative slope at just a point. So here, the car is going from a positive slope to a zero slope to a negative slope to a zero slope. So nope, I don't see any moments of instantaneous rest. So basically, I see that 3 to 7 seconds the car is at rest, 9 to 12 seconds the car is at rest. So that means the best answer for this problem is A and C. At point B, at 8 seconds, which is answer choice B, the car is cruising backward at a constant negative velocity. So you can see right before t equals 8 seconds, the car is cruising backward with a negative velocity, with some rapid negative velocity, and right afterward, it's cruising backward with the same negative velocity. So 8 seconds is not a moment of rest. I was just trying to fool you. What is happening at 8 seconds? Why is it crossing the x-axis? I'm sorry, the horizontal axis. Why is it crossing the time axis at t equals 8 seconds? That just means that it's passing the origin. It's passing the position x equals 0. That's all that's happening at that time. So in other words, imagine a mile marker stuck by the side of the track saying, here is the mile marker x equals 0 meters. And the car is just blasting right past it in reverse from before that point to past that point. All right, let me clear our graph a little bit here. And let's consider part B. So part B asks, all right, during which time interval is the car moving backward? All right, well then let's think about what would that look like again, algebraically or mathematically on this graph? The car is moving backward whenever it's going from a more positive position to a less positive position, right? Or in other words, when the position is becoming more negative over time, right? So x is becoming more negative over time. What does that look like graphically? That means that this graph is going to have a negative slope. And if we think about that, remember what the slope represented, right? The slope on this graph is rise over run. That's average velocity. Oh, so that also means that we have a negative average velocity. Okay, so that makes a lot of sense, doesn't it? Remember what we said earlier? When the average velocity of an object is positive, that means its net motion over that time interval is in the positive x direction. But when the average velocity of something is negative, that means its net motion over that time interval is in the negative x direction. Okay. Now it turns out over each one of these sort of 4 time intervals here, if we sort of think about this as being time interval A, B, oops, a little too far there, C, and D. then over each one of these time intervals, you can see that the slope has one continuous positive value. So what that means is, even though we're talking about an average velocity over each of those time intervals, the average velocity is the instantaneous velocity at every point during one of those time intervals. The only time that'll be different is if we try and take some average that crosses between the time intervals. Okay, well, that's all right. That's lots of analysis. Let's answer the question. The question is asking, during which of the time intervals is the car moving backward? It would be any of the time intervals during which the position is becoming more negative over time. Put another way, that's when it has a negative slope. So it looks to me like that's happening during only time interval C. That's when the position is becoming more negative over time. So it's just 7 to 9 seconds. So the best answer choice here is both A and B, but not C. Okay. What is happening during time interval C down there? Why is the graph in negative territory? Is it because the car is moving backward? No. The car during that time interval is just parked at a negative position. So it's parked steadily at a position of negative 3 meters, and it's just sitting there somewhere to the left of our origin. But it's not moving backward. It's just sitting out there in negative territory, parked. All right, then finally, this problem wraps up with some calculations. So first I ask, what's the average velocity of the car during the entire 12-second time interval? And I ask what's the average speed during that same entire 12-second time interval? And then I ask you to compare the average speed and average velocity over just a short segment of the graph. So just that third segment, 7 to 9 seconds. So let's, why don't we just take these in reverse order? Okay, let's do F first. And notice, by the way, I've skipped part E, so I'll leave that to you to work on your own. So for part F first, the average speed and average velocity. Let's remember our definitions here, okay? So average velocity first is going to be equal to displacement over time. So now let's spell out what displacement is. It's going to be the position at the end of the time interval minus the position at the start of the time interval. So that's position at 9 seconds minus position at 7 seconds. And then it's the length of the time interval, right? So it's the 7 to 9 second time interval, right? So let's spell that out. This is a level of detail you don't normally need to show, but I'm trying to be extra explicit here. Okay, so the position at 9 seconds is down here on the graph. Here's 9 seconds, and the position is negative 3 meters. So that's negative 3 meters. And then I subtract from that my position at 7 seconds, and that was up at positive 3 meters. Okay, and then delta t from 7 to 9 seconds is, of course, 9 minus 7. So in my numerator, I have negative 6 meters, and in my denominator, I have positive 2 seconds. Remember, delta t is always positive. All right, so that means that my average velocity during this time interval is going to be equal to negative 3 meters per second. By the way, I spelled out here in this problem, express your answers to 2 significant figures because, well, this is where an example of a problem where I'm giving you a graph to read. And it's not really clear when you just look at like the values on the axes, how many significant figures are the axes labeled to. So I'm just making a request. I'm just saying, all right, look, read the values off the graph as best as you can, and then round your final answer to 2 sig figs. Let's assume you know the answers to 2 sig figs. Okay, oops, I made a mistake and I have one of these to 3 sig figs. Fine. All right, so that's why, because you're reading a graph. So so I spelled it out. When you're going to have problems where I give you the positions or I give you the times, then you should just look at the number of digits, significant digits that are on those values, and then use our rules for multiplication and addition, subtraction, and multiplication, division that we learned already. All right, let's take a look at the average speed. So first of all, average velocity. So now we know the answer is negative 3. Okay, so now let's take a look at average speed. So I'm going to remind myself my formula. Average speed, oops, pen, average speed is equal to distance traveled, right, over this time interval. So this is the 7 to 9 second interval, right? Or I could have labeled that time interval C. That would have been nice if I had labeled that, okay? And then I have the time interval from 7 to 9 seconds, okay? All right, so distance traveled is going to be, what is it in this case? There's no, if the object is moving in a straight line and doesn't switch direction, then I can just take the absolute value of the displacement. Is that true in this case? Yeah, it looks like it is. It looks like the object goes from 3 to positive 3 meters to negative 3 meters in a straight line without switching direction. Okay? And by the way, it's not because the graph is straight, it's because the track is straight. But it doesn't switch direction, right? The graph doesn't zigzag, right? So that means I can take the absolute value in this case of the displacement during that time interval. And that's going to be the absolute value of 6 meters, okay? A negative 6 meters, pardon me, divided by 2 seconds. And that's equal to positive 3 meters per second. And of course, good. All right, let's reflect. Is the speed positive? Yes, good. Right, it always needs to be. So speeds must always be positive. So we have a speed of positive 3 meters. Okay. So that makes sense, right? Remember, under what conditions is average speed and average velocity, are they the same value? Or in this case, just the absolute value of each other, right? And that is when you have an object whose motion never changes direction. So it's along a straight line path with no doubling back. Okay, so no change in direction of the motion. In that case, average speed and average velocity will be the same, or at least the same to within a factor of -1. Is that true for the entire 12-second time interval? No, absolutely not, right? Over the entire 12 seconds, this car definitely changes direction, right? It goes from moving forward during the first time interval to moving backward during the third time interval with sort of stops at rest before and after, or in the middle and after. So we would expect these two values to differ. All right, so let's go ahead and calculate them and find out. So average velocity over the entire time interval is going to be equal to displacement over the entire time interval over the time of the entire time interval. That's going to be equal to x12 minus x0, right? So the position at 12 seconds minus position at 0 seconds minus delta t over the entire time interval. So looking at my graph, I can see that the position at the very end is -3 meters. The position at the start, the position at the start is 0 meters. And then the entire time interval is 12 seconds, 12 minus 0, right? I can spell that out. So that's going to be equal to -0.25 meters per second. Let's calculate the average speed over the entire time interval. Okay, so the denominator is pretty simple. It's 12 seconds again. That's familiar. The numerator is more complicated. What's the total distance traveled over this entire 12 seconds? Well, we don't have a formula for that. So we just have to sort of use our common sense. It'll be equal to the distance traveled during each of the individual time segments, right? So 0 to 3, 3 to 7, 7 to 9, 9 to 12. And I can see by inspection that we know that the car is parked at rest during time interval B, so that's 0, and during time interval D, that's also 0. So what that turns out to be then is 3 meters during the first time interval, 0, -6, but these are distance traveled, so it's always positive, right? We take the absolute value, and 0 over 12 seconds. So that's 9 meters over 12 seconds, and that's 0.75 meters per second. Positive? Yes, because speed is always positive. Average or instantaneous, it has to be positive. So that means our final answers are negative 0.25 meters per second for the average velocity and positive 0.75 meters per second for the average speed. So problem 3 is very similar to problem 2. It's another graph I give you that shows the position versus time for the car, for another toy car on a different track, but it's still very similar. And I started off with a couple of conceptual questions asking about the motion of the object. And then I ask you to do some similar calculations for average velocity and average speed over either sub-intervals of the time or the entire interval of the time. Okay, so I'll leave it to you to try those yourself. And whenever you're comfortable with the tutorial problems for practice, then please go to online homework 3 and do the problems for credit that are similar to all of these. And that's it for lecture number 3. So in lecture number 4, we're going to continue these same graphs of position versus time and velocity versus time, but we're going to expand on it just a little more with that idea of slope and area under the curve, and then we'll do some examples on tutorial 4. All right, great. I'll see you for lecture 4.